Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. So, in this lecture, we are going to discuss the topic memory reference instructions. So, already we know the instructions are classified into mainly three types, that are register to register reference instructions, and second one is the input or output reference instructions, and the third one is the memory reference instruction. So these are the three main reference instructions. So now we are in this lecture we are going to discuss about the memory reference instructions. So that means the instructions that are related to the memory. Okay. So the basic computer, it has a 16-bit instruction register. So if you look into the architecture of the computer, inside that there is a 16-bit register that is called instruction register. So the purpose of the instruction register is it can be used to store the instruction currently executing instruction. So we can place the currently executing instruction in the instruction register. So which can denote either the memory reference or register reference or input or output instruction. So mainly already we have seen, so the instructions are classified into three types. Either that may be a memory reference instruction, a register reference instruction, or input or output reference instruction. So here we are discussing the memory reference instructions. So these instructions, it refers to the memory address as an operand. So the other operand is always the accumulator. So suppose if you are performing any operation, definitely it requires two operands. So the one of the operand is it will be stored in the accumulator, and the other operand will be stored in the memory. So using the two operands, it will perform some certain operation. Okay. So see here. So it specifies a 12-bit address and 3-bit opcode and 1-bit addressing mode of direct and indirect addressing. So if you look into the size of the address register, so the size of the address register is 16-bit length. So that means 0 to 11. So 0 to 11. So total it represents a 12-bit. So 12-bit address. So this 12-bit it represents the address of the operand. And next 3 bits. So next field is the opcode field. So opcode field is it represents total 3 bits we are using. So 12th bit, 13th bit, 14th bit. So these 3 bits it is used to represent the opcode. So opcode means it specifies the operational code. So what type of operation it has to perform, that will be determined by using this opcode bits. And the last bit is the 15th bit is it will be represented with I. So that means indirect bit. So it can be used to decide whether the instruction is having direct address or indirect address. So if I is equal to 1, then that is a indirect address, and if I is equal to 0, that is a direct address. Okay, so this is about the instruction register format. So using using this opcode field, so using this 3 bits, we can decide whether that is a register reference instruction or memory reference instruction or the input output instruction. So see here. Okay, so this is an instruction register. So here these are the 12th bit, 13, 14. So these are the 3 bits. So by decoding that 3 bits opcode bits, we can decide whether that is a memory reference instruction, register reference instruction, or IO instruction. Okay, so see here. So how we can decode here. Okay, so this is the 12th bit, 13th and 14th bit. Okay, so here, so first value, so first So here total the number of bits are 3. So that means total we have 2 power 3 input combinations. So 2 power 3 combinations. So what is the first combination? When all inputs are zeros. So the corresponding decimal value is 0. So when all the inputs to the 3/8 decoder are zeros, then it will generate a control signal D0. Okay. Next sequence is a 001. So when input combinations are 001, then the 3/8 decoder, it will generate a control signal D1. Because in order to perform any operation, we require both the control signals and the timing signals. So the control signals are generated by using this 3/8 decoder. Similarly, the timing signals are generated by using a sequence counter. So this is a 4-bit sequence counter. So using that 4-bit sequence counter, it will generate 16 timing signals. So that 16 timing signals are T0 to T15, and the control signals are D0 to D7. So using that timing and control signals, the corresponding operation will be performed. So D0 to D1. Next one is a 010. So 010. So it will generate a D2 control signal. So similarly, it will perform all the operations. So the last case is when all inputs are logic 1, it corresponds to the decimal value 7. So during that input case, it will generate a control signal D7. So see here. So from the D0 to D6, D0 to D6, it corresponds to memory reference instructions. Memory reference instructions. And D7. So based on the D7, so D7 is a register reference instruction or input or output reference instruction. Okay. So D0 to D7, D0 to D6. That is a memory instruction, memory reference instruction. Next D7. So if the D7 is equal to 1, if D7 is equal to 1, so D7 is equal to 1 means if the all input combinations are logic 1, then that corresponds to either register reference instruction or input or output instruction. Coming to the second one, register reference instruction. So these instructions, it performs operations on registers rather than memory addresses. So the IR of 12 to 14 is 111. So for this register reference instruction, the opcode bits, that means 12th bit, 13th and 14th bit should be equal to logic 1. And IR of 15 is equal to 0. So here you can see, so the 15th bit of IR, instruction register. So this is a instruction register. So for this register reference instruction, so the 15th bit should be 0 and the 12th, 13th, 14th bits of the opcode bits corresponds to all ones. So then only it is called register reference instruction. So see here. So note, so the bit in 15, position 15 of the instruction code is designated by the symbol I. But it is not used as the mode bit when the operational code is equal to 111. So basically, this 15th bit we are using to decide whether that is a direct address, the instruction is having direct address or indirect address. But here, when the opcode bits are all equal to 111, this 15th bit we are not using as a mode bit. So here, if this 15th bit is equal to 0, then that means that is a register reference instruction. Similarly, if the 15th bit is equal to 1, then that specifies the instruction is having input or output instruction. Okay, so this is a second type of the instruction, register reference. And the third one is a input or output instructions, input or output reference instruction. So for this, the 15th bit of the instruction register should be logic 1. And the opcode bits of the instruction register, that is 12th, 13th and 14th, should be logic 1. So then the type of instruction is called input or output or reference instruction. So now we have seen the classification of the instruction. Okay, now we are going in detail about the memory reference instruction. So the memory reference instruction. So the opcode bits are from 000 to 110. So these are called memory reference instructions. So the memory reference instructions are useful in order to perform the operations on operands, and that operands are stored in the memory. And memory reference instructions are those commands or instructions which are in custom to generate a reference to the memory and approval to the program to have an approach to the commanded information, and that states as to form where the data is cached continuously. So these instructions are known as memory reference instructions. So using these memory reference instructions, we are performing some operations related to the memory. So total here, using this memory reference instructions, total we can perform 7. So total 7 memory operations we can perform. So that are AND operation, add operation, load accumulator, store accumulator, branch unconditionally, branch and save a return address, increment and skip if 0. So these are the different instructions. So these are all the different memory reference instructions. So using that memory reference instructions, we can perform all these operations. So let's start with one by one. So see here. So we can perform total 7 operations. 7 operations: AND operation, add operation, load accumulator, store accumulator, branch unconditionally, branch and skip, branch and save return address, and increment and skip if 0. So these are the different memory reference instructions. So how we are deciding? So how we are performing? So at a time we are performing only one operation. So which type of operation we are performing, that depends upon the opcode bits. So the opcode bits are 12th, 13th, 14th. So using these 3 bits, we are deciding which operation it has to be performed. Okay, so see here. So when all input combinations are 0, 0, 0, then it will perform AND operation. So it will perform the AND operation. So in order to perform this AND operation, it requires both the control signals and the timing signals. So both it require. So then only we can perform this particular operation. Okay. So see here. So first one is a AND operation. AND. So the AND instruction, it implements the AND logic operation on the bit collection from the register, and the memory word is determined by the effective address. So the result of the operation is moved back to the register. Okay. So here we are performing the instruction is the AND. So it is a first memory reference instruction. AND. So it performs the logical AND operation between the operand stored in register accumulator and the other operand that is stored in the memory. Okay. Okay. So see here. So already we know that in order to perform this operation, we require both the control signals and the timing signals. So the control signals are represented with D, capital D, and the timing signals are represented with T, capital T. Okay. So we require both the control signals and the timing signals so that we can perform that particular memory operation. Okay. So see here. So see here. So here the during the D naught and T naught. So during T naught and D naught. So already we know. So the programs we are storing in the memory, and from the memory the instructions will be fetched. So in order to understand, let's see a flowchart of the instruction cycle. So what will happen? So in the memory we are storing a program. So see here. So the first instruction is a and AL comma BL offset. So BL we have written in the bracket. So it indicates that it is a memory reference instruction. So the first instruction is stored in the 4000. So when the sequence counter is initialized to 0, so when we apply a clock pulse to the sequence counter, then the timing signal T0 will be generated. So during T0, what will happen? So the program counter address will be loaded into the address register because the instruction has to be fetched from the memory. So instructions has to be fetched from the memory. So in order to fetch this instruction, first we require the address of the instruction. So that's why, so this address is stored in the program counter. So that's why first the program counter address we are loading into the address register. So that that operation will be takes place during T0 cycle. So that is the first cycle. After applying one more clock pulse to the sequence counter, it will generate a next timing signal. So that is a T1. So during T1, what will happen? So the instruction, it will be placed in the instruction register. Okay. So how we can store the instruction in the instruction register? By specifying M of AR. That means it specifies the offset address. Okay. So in this address register, it has stored the address of the instruction. So using that address, the instruction will be placed in the instruction register. Okay. So after that, we have to increment the program counter. So that means now the program counter, it stores 4001 because whenever the first instruction is fetched from the memory, after that it will be decoded and then it will be executed. So after the first instruction is executed, the next instruction has to be fetched from the memory. So that's why we are storing the address of the next instruction in the program counter. So that will takes place during the second, that means T1 clock cycle. After T1 clock cycle, if you apply one more clock pulse to the sequence counter, it will generate a timing signal T2. So during T2, what will happen? The instruction. So whatever the instruction we will place in the instruction register, that will be decoded. Okay. So decode is nothing but the instruction which is written in the human language, that will be converted into the machine language. That means in the decoding phase, it will interpret the instruction. It will determine what type of operation it has to be performed. Okay, so that is a decoding. So the decoding will take place during the clock cycle T2. And after that, so see here. So during T3, M of AR, so the effective address after decoding, so the effective address of that particular memory location will be placed in the address register. Okay. So after T3, so next T4 is there. Okay. So these are the different timing signals, T0, T1, T2. So during T0, what will happen? The program counter address will be loaded into AR, and after that the instruction will be, so first during T0 the instruction will be fetched. After fetching, the instruction will be placed in the IR register, and after that decoding, decode, fetch, decode, and after that execute, after that execute. So this fetching and decoding, it is common for every instruction. Okay, so we have seen T0, T1, T2, T3. Okay, so see here. So during T0, D0, T0. So during T0 cycle, the program counter address will be loaded into the address register. During T1, the instruction will be placed in the instruction register and program counter will be incremented. During T2, the instruction is decoded. So how we are decoding? So using the bits 12 to 14, because for every different combinations of these 12 to 14 bits, the operation will be different. So for this for AND operation, the 12 to 14 bits, all bits will be zeros. Okay. So in this way, we are decoding the instruction. During T3, the effective address of the memory will be loaded into the address register. During T4, the data which is present in that memory location will be copied to the data register, because here see we are performing the AND operation. So on what registers we are performing the, on what operands we are performing the AND. In order to perform this AND operation, we require two operands. Operand 1 and operand 2. We are performing AND operation. Okay, so we are performing the AND operation between the accumulator register, between the data register and memory. Okay, we are performing the AND operation between the accumulator and the data register. Okay, initially we are performing this AND operation between the accumulator and the memory, but we cannot perform directly the AND operation with the memory. So that's why first the data from the memory we are loading into the data register. First we are copying the data from the memory location to the data register, and after that we are performing the AND operation between the data register and the accumulator. Okay, so here we are using the registers accumulator and the data register. Okay, so that's why during T4 the memory of AR, so whatever the data present in the memory location, the address is specified by the address register, it will be copied to the data register. After copying to the data register, during T5, so we are performing a AND operation between the accumulator register and the data register. So finally, after performing the AND operation, the result will be stored in the accumulator itself. After execution of the AND instruction, the sequence counter will be initialized to 0, so that the next instruction will be fetched from the memory. So whenever the sequence counter is initialized to 0, again the next instruction, it starts with the timing signal T0, T1, T2, T3, T4, so and so on. So this is a AND memory reference instruction. And coming to the second one, so second memory reference instruction is a add. So add. So this add instruction, it performs addition operation between two operands. So one value is stored in the one value similar, so same operation. So add operation. So it performs the addition operation. For this addition operation, one operand is stored in accumulator and another value is stored in the memory. But we cannot perform add operation directly with the memory. So that's why what will happen first from the memory. So see here. So the memory will be like this. So here some data is there. Some data is there 05. Okay. So and in accumulator some 04 is there. So can we perform add operation directly with the memory? No, it is not possible. So that's why what we are doing. So whatever the data present in the memory, first we are loading into the a data register. So we are copying to the data register. So what is the value present in the memory location? 05. So that 05 we are loading into a data register. After that, we are performing a AND operation between the accumulator and the data register. So between these two registers, we are performing the add operation. Okay. So during T1, T4. So during T1, during D1. So because for this add operation, the input combination is 0, 0, 1. So this is a 12th, 13th, 14th. So 0, 0, 1. When 12, 13, 14, 0, 0, 0, then it performs AND operation. Okay, so this is D naught. Next 0, 0, 1. So this is the control signal D1 and the operation is add. So in order to perform the add operation, we require the control signal D1 and the timing signals. So D1, T0, T1, T1, D1, T2, D1, T3, D1, T4, D1, T5. So during T0, what will happen? The program counter address will be loaded into the address register. So just before we have seen for the AND operation, AND instruction. Next, after placing the program counter address to the address register, then what will happen? So it will place the M of AR. So it will place the instruction from the memory into the IR register, instruction register, and after that the program counter will be incremented. So PC plus 1 will be stored in PC. Okay, so after that it will be decoding. So like that, all these operations will be takes place from T0 to T3. So during T4, what will happen? So the data, so this operation, whatever the data is present in memory location, that will be copied to the DR. So that is a T4. During D4, that operation will be performed. And during T5, that operation will be executed. So during T5, so D1, T5. So what is the operation? Addition operation. What is addition? So here we are performing addition operation between the contents of the accumulator and the contents of the data register. So that is the operation. So in addition, so when you are adding any two operands, there may be a chance of getting the carry. So if there is any carry, then that carry will be stored in the E. E means extended flip-flop. Okay. If there is any carry generated, that will be stored in the extended flip-flop. After that, the sequence counter will be initialized to 0. So that the next instruction will be fetched from the memory. Okay. Next one. So this is a next one, load accumulator. So load accumulator. So that means this is a 0, 1, 0. So that it is corresponding to D2. Okay. So during this D2, it performs LDA, load accumulator. So see here. So see here. So this load instruction it shares a memory word denoted by the effective address to the register. So that means in a memory we have a word. That word we are copying to the register. So we are transferring the content from the memory to the register. So that is a load accumulator. Load operation. So load means copying or transferring the content from the memory to the register. So that is nothing but loading. So load accumulator. So we are loading the accumulator register with the contents from the memory word. So here, see here, we have a some value, some 08 is there. So the address are 4000, 4001, 4002, 4003, and this is a accumulator register. So already we know during T0, T1, T2, T3 cycles, the instruction will be fetched from the memory, then decoded, and it will be determine what type of operation it has to do. After T4, so from T0 to T3, it is common for all the memory reference instructions. Only from the during T4, the operation will change. So during T4, what will happen? So M of AR to DR. So here, this is a data. 08 is present in the address. So AR. So in address register, we have a 4001. Let us assume address register is 4001. So we are going to the memory location, 4001 location. So in that, we have a value or operand of 08 that will be copied to the accumulator. So after performing this load accumulator, the contents of accumulator is 08. Okay. So because we cannot directly taking from the memory to the accumulator, so that's why first this value we are placing in the data register. First we are taking into the data register. This is data register 08, and from the data register we are copying to the accumulator. So this one. So after that, the sequence counter will be initialized to the 0. Next, store accumulator. Store accumulator. So this store accumulator, it saves the contents of the register into the memory word that is defined by the effective address. So this store accumulator operation is opposite to the load accumulator. So in store accumulator, we are storing the value from the register to the memory. So we have a register accumulator and we have a memory. Okay, let us assume here this is 4000. So let us assume this is 40, this is 12, 25, 43, 82. So these are the contents before the store accumulator operation takes place. Okay. So see here, store accumulator. So the accumulator, it contains the value 40 and the memory it contains 12 in 4000 location, 25 in 4001, 43 in 4002, 82 in 4003 location. So see, so during T3, T4, what will happen? The accumulator content, it will be loaded into the memory. So see here. So let us assume some address register, it contains some 4002. If the address register is 4002, then the content to 40 we can transfer to this location. So after transferring, after performing this store accumulator, the contents of accumulator will be transferred to this location 40. So after execution this, after performing this store accumulator, the contents of the 4002 location will be 40. So this is called store accumulator. That means the value of accumulator we are storing into the memory, and whose address is specified by the this address register. Next, fifth one, bun. So shortly we can call BUN. So branch unconditionally. So branch unconditionally instruction, it transfers the program to the instruction specified by effective address. Okay. So see here. So we have a memory. Okay. So the instructions are, addresses are 400. Okay, so see here. So branch unconditionally. So the name itself, it specifies the meaning unconditionally. Branch unconditionally. So that means branching. Branching means transferring program control from one memory location to the another memory location without checking any condition. So let us assume if the program control is at the location 4000. So now it is required to transfer to the 4500. So when this instruction is executing, the program counter it holds 4001, while the instruction of this 4000 location is executing. So the program counter is loaded 4001. But now we need to transfer to a new location. So that is 4500. So that this new location address 4500, it will be, we have to load into the program counter, so that the instruction which is available at the 4500 location will be gets executed. So that's why this address, so 4500 is the address 4500. So this 4500 we have to load into the a program counter, so that the program control will be transferred from 400 location 4000 location to the 4500. So this is called branch unconditionally. So that means here branching takes place from 4000 location to 4500 location. So here we are not checking any condition, simply unconditionally the branching takes place. So that's why it is called branch unconditionally. So next memory reference instruction is the BSA. So branch and save return address. So this instruction can branch a part of program known as subroutine or procedure. So this branch and save return address, especially we are using when we have a subroutines. Whenever we have a subroutine, the program control will be transferred from main program to the subroutine, and then the statements in the subroutine gets executed, then returned back to the main program. So for that purpose we are using this instruction, branch and save return address. So whenever the program control is transferring from main program to the subroutine, so we are storing the address. So we are storing the address of the next instruction of the main program. Okay. So for that purpose we are using this branch and save return address. So see here. So during T4, the operation will be takes place. Program counter address will be storing to the M of AR. We are storing into the memory. Okay, so that we can understand with a diagram. So the figure A, it represents the contents of the memory and program counter before BSA instruction execution. And the figure B, it represents the memory and program counter contents after execution. Okay, so in the memory we have a address 20. We have a address 20. In that address we have a instruction BSA. So 0. So this instruction 15th bit is 0 and opcode is BSA and address is 135. So first 15th bit is I is equal to 0. Okay, so that means I is equal to 0 means that is a direct address. So there here given the direct address. So address of the operand is given directly 135. So Now this is a 135. So address is 135. Okay. So here the program counter value is 21 because when the instruction which is available at 20 is executing, the contents of the the address of the next instruction will be stored in the program counter. So that's why the program counter address is equal to 21. So now in the address register is holding 135. Okay. Next we are incrementing the address register 136. Now see. So first the program counter address will be we are storing into memory. So the program counter address. What is the program counter address here? 21. So that we are storing into the memory specified by the address register. What is the address register? 135. So this we are storing into the 135 address. So in 135 address, what is the value we have stored? 21. Okay. After that, we are incrementing the address register. So what will happen? So 135 becomes 136. So in 136, we have a subroutine. So all the statements in the subroutine gets executed, and the last one is a 1 BUN. So 1 BUN. What is this one? That one means indirect address. So what this 135? The 135 is not the direct address. It is an indirect address. Okay. What is the instruction here? Branch unconditionally. So that means this 135 it doesn't contain. It is not the address of the operand. Okay. So we need to calculate the effective address. So for that purpose, we need to go to the 135 location. So in that 135 location, we have a return address. So using that return address, the program control can shift from the subroutine to the main program. So see here. So after execution, what are the contents of the program counter? It is 136. So before execution, the program counter is 21. But after execution, program counter value is 136 and the return address. So this is the return address. Okay. So from this instruction here, the program control actually it is at the 20. But now from the 20, it is transferred to 136. So in 136 location, we have a subroutine, and after executing that, again it is going back to the 21st memory location. Okay, so using this BSA instruction. Okay, and last memory reference instruction is a ISZ, increment and skip if 0 instruction. Okay, so this increments the word specified by the effective address. Okay, so using this instruction, we can increment the memory word which is specified by using the effective address. And if the incremented value is equal to 0, then PC is incremented by 1. So a negative value is saved in memory word through the programmer. It can influence a 0 value after getting incremented repeatedly. Thus, the PC is incremented and the next instruction is skipped. So since it is not possible to increment a word inside the memory, so increment operation, we cannot perform the increment operation directly with the memory word. So suppose if you have a memory word, so you have some 8. Okay, so we cannot directly increment this memory word. So for that purpose, what we are doing, first this memory word we are copying to the data register. After copying to the data register, then we are performing increment operation on this data register. Okay, and after that, okay, so it is necessary to read the data word into the data register, and after that we are incrementing the data register. then we are storing that incremented data register value back to the memory word. Okay, so 08, so it is copied to data register 08. After that we are performing the increment operation, so 08 becomes 09. So now in the data register, so 09 is there, so that 09 again we are loading it back to the main that memory word. So the 08 is overwritten with 09. So in this way we can increment the memory word. Okay, so increment and skip if 0 instruction. So suppose after performing the increment operation, if the memory word becomes 0, then that instruction will be skipped. So here 09, that means we got a non-zero value, so that the instruction will not skip. Suppose if the after incrementing, if the memory word is having 0 value, then that memory location will be skipped. Okay, so during T64, first M of AR will be copied to the DR data register. So M of AR is this one. Let us assume 4000 location. So in 4000 location 08 is there. So 08 is loaded into data register. After that we are incrementing the DR data register value. So DR plus 1. So that means 8 plus 1. So 9. So that incremented value will be stored in data register. From the data register we are moving back to the memory. So data register to M of AR. Okay. So this is an operation. So this is a increment under skip if 0 instruction. So these are the flowchart for memory reference instruction. So till now we have seen undo instruction, add instruction, load accumulator, store accumulator, branch unconditionally, branch and save return address, increment and skip if 0. So these are all the different so this will happen in D0 to T4, during T1, D2, D3, D4, D5, D6. So total we can perform 7 operations. So total we have performed 7 memory reference instructions. So in this lecture we have seen classification of different instructions, and in detail we have discussed about the memory reference instructions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.